Hi everyone, today I'm going to introduce a paper named Stochastic Depth Ambient Occlusion. Continuing on from last time, I chose to deal with the same topic, which is ambient occlusion. But this time the paper is a relatively recent one, and I believe you will understand more about how ambient occlusion works in real-time rendering after you take a look at it. Before we move on, let's take some time to review what we've discussed in the last presentation. Ambient occlusion is a technique that mimics real-world phenomena such that occluded space gets darker and shadowed. We can calculate how much each point in the scene is occluded by ray casting, but doing so is usually expensive, especially when it's done in real time. And yes, this time again, we are going to see how ambient occlusion can be done without degrading much performance and artifacts. From the next slide, I will show the previous works contributed to today's paper. There are mainly three papers the authors were inspired from. For now, you don't have to look carefully at how those papers had contributed to the paper, but please focus on the keywords and I'm going to explain more. I'm not going to talk much about the third one though, because simply grasping the idea will be enough. In the last video, we've already talked about HBAO. In HBAO, for a single point on the surface, it shoots several sample rays in many different directions, which march along the surfaces. Walking along the surface, each ray keeps updating how much it is elevated compared to the beginning. This elevation is later compared with an angle between tangent on the point and world horizon. The bigger its difference is, the more occlusion value the point is given. But still, just like SSAO from last video, HBAO also relies on depth buffer. And you know that depth values depend on the viewpoint. Therefore, the original HBAO cannot capture the surface point's occlusion because some part of the geometry can be ignored in some viewpoints. In the image on the right side, some geometry in the scene keeps changing its color as the character gets closer. This is exactly what happens when the hidden geometry is revealed after the camera moves, and such artifact is called AO pop-in. The next reference talks about how to deal with this problem. What if we know the hidden geometry in advance and consider it when calculating ambient occlusion? To do so, a method using A buffer was suggested. A buffer is a buffer storing multiple fragment data for every pixel. If you remember what depth buffer is, in the rasterization process, the depth buffer keeps dropping the fragments that are going to be occluded and leaves only one data for each pixel. But A buffer does not, which means that it contains the data from occluded fragments as well. In the first image on the right side, you can see the arch obscures the wall behind itself and the occlusion is ignored as a result. But if we can access multiple geometry layers, such artifacts can be removed. To help you understand more about what geometry layer is, I brought some pictures. It's nothing but seeing through the whole scene and organizing all the topography in the order of being observed. I believe you've already figured out how today's paper settled the problems in AO, and now is the time to look at it carefully. The second previous work actually has some problem. Using the first n visible layers either requires multiple render passes or has large memory requirements. Therefore, it's not suitable for real-time ambient occlusion. And here is how the third one contributed to this work. What if we don't use an ordered list of the layers, but instead use a random subset of the layers? And how will it make a difference? Here, the stochastic depth map is proposed as a key element for this method. Stochastic depth map is a multi-sample texture containing multiple samples of random depth values per pixel. Because it's a texture, its multiple samples can be fetched from shaders. To put it simple, it's a texture which contains multiple samples and each sample contains random subset of depth values like first, third, seventh, and ninth scene layer. And all sample locations are set to the pixel center so that we can store all samples in a single render path. This eliminates the need for complicated calculations when sampling, so it has an advantage in performance. Generating the sample and constructing stochastic depth map can be done in many ways, but here I will show you the very basic, simple, easiest solution of using hash function. First, generate a uniformly distributed random number between 0 and 1 for every fragment using hash function, where the pixel location, sample index, and sample depths are its seeds. These values are then compared to a global transparency value alpha. It's like if it's bigger, keep it, and if it's not, we discard it. Because the numbers are random, doing this process yields some random subset of the fragment scene layers. Please remember that this is fragment-wise, so we are actually not constructing continuous scene layers. And also remember that in practice, more sophisticated methods are used to avoid over or under representation of certain layers. The reason that I'm not talking about the method used in this paper is that it's not that important and there is a concern that things get more complicated. After constructing stochastic depth map, you can extend HBAO. On the left side of the image, because the hemisphere is not big enough, the marching ray does not catch the spherical geometry under the cube, and therefore the occlusion is completely ignored. But if we introduce stochastic depth map, you can see that some samples contain the depth values that are on the surface of the spherical geometry, and the marching ray catches the geometry and marks it as an elevation, leading to the increment of the occlusion size. Aside from the basic idea, here are some heuristic and improvement applied. First one is for sampling efficiency. Suppose that we have a simple geometry such as a flat surface with only one layer. Then using the simple HBAO or using only the regular depth buffer will be enough. In this paper, such condition is checked to decide whether it is required to retrieve multiple depth samples or not. This is important because multiple sampling is basically more expensive and therefore won't be always the best choice. And the second one is considering multiple viewpoints. Stochastic depth ambient occlusion itself cannot avoid the AO pop-in artifact that I mentioned in the beginning. To solve such problem, we can use secondary stochastic depth maps generated from different viewpoints. In the image, you can see that if the face of an object is completely parallel to the view direction, the occlusion may not be captured. Here are some results provided by the paper. You can see that the computation time gets bigger as the more samples are used, but things get aesthetically better. The rightmost image is the result of the simulation using full depth field setup layers. But in some cases, using more samples can yield missing occlusion. This happens when there are many layers existing between an occluder and the camera, and many samples are dissipated, not capturing the occluded object. Adding a compensation multiplier can restore some of the missing occlusions. Thank you, and this is the end of today's video.